And recording. Okay, I hope it's working. Yeah. All right. Good morning, everybody. Thank you all for coming in today. Can you hear me and see me okay?
Yes.
Cool. Yeah, as Alexa said, we kind of like overslept, so I'm kind of like still not fully focused, but I think it should be okay.
You overslept.
I overslept, yes, something like that. So today I'll cover Reconcile, basically how to do Reconcile by yourself and the math behind it. The idea was actually to create both ways. So Reconcile on one way, which is projecting 3D point into 2D screen space, and vice versa, which is to have a point in 2D screen space and convert it back into a 3D space, like Carto Track or other tools like that. If anybody have. I don't know if we'll have time to cover all of it, but we'll just start and see how it's going. So the reason that I chose this specific thing, I think I'm kind of like still iterating when I'm doing the workshops over here. I'm still iterating around the concept of projections and wall position and matrices. And I don't know if any of you were in the classes before about matrices. I was talking about the world matrix and I was trying to explain that. Sometimes when we solve camera tracking, this specific matrix, this guy over here that I was trying to explain last time, this guy is called the extrinsic matrix, which means the external matrix. It's just a matrix that basically holds the position in space. It only have the location and rotation of the camera or X or whatever it is, okay? Today I will not talk about matrices, but it's basically the second part of it, to the entire kind of like engine to convert 3D point into 2D space, which is the intrinsic matrix. This matrix kind of like explains the internal elements of the camera. So like the focal point, focal plane, or the resolution, different things basically that define the camera itself. And that's actually what we need to convert 3D to 2D. So with that in mind, let's start. So basically I have this very basic thing. I'm going to start from scratch so you can see what I'm doing. I brought a scanline over here. I brought a camera. And I'm going to connect it as well, of course. Camera. Okay. And I'm going to leave the camera at 0, 0. So my goal basically is to create the most simple case to convert a 3D point to this screen, and then basically add one step at a time and try to explain it. It's not as complex, but that's what I'm going to do. So it's going to be the simplest case. In the camera, I'm going to choose over here the focal length of 1, aperture of 1, and vertical aperture as well on 1. So this is a kind of like a special case for us, which we'll see in a second why is that. And it's very convenient for us. So I'm going to put everything on 1. And then I'm going to bring an axis over here. And I'm going to put it on -1. So it's just 1 unit away from the camera. Okay? I'm going to bring a scene so I can actually combine everything. Also, I'm going to put a resolution of 1000 pixels. And I chose it again because now kind of like everything is aligned. It's not like weird format. It's not anything that it's confusing for us. Everything is as easy as possible to solve this specific case that I can build upon. And I'm also going to bring a card over here. I'm going to put it on just 1 unit. And it's also on -1. So, and then I'm going to go over here and I'll remove our grid so we can see what we're doing. Okay. And I'm probably missing something. Yeah, there it is. Okay. So this is our most basic case that I want to try to solve. So the reason that I'm actually choosing this -1 over here, this is kind of like representing our image plane. So this is kind of like would be if we have a camera obscura and a pinhole. This will be kind of like an image plane as 1 unit, like how it would sit on the sensor. So this is kind of like define how everything will converge on our sensor, basically our renderer or whatever it is. Okay, so it's kind of like tells us what's the boundaries of our image that we need to think about. That's why I chose this thing to be like that, -1. And this is our case over here, and I'm going to bring the axis, and I'm going to create a transform over here. So, as I said, special case, camera at origin, focal distance, horizontal aperture is on 1. By the way, if you didn't know, I'm going to say it again. New camera don't care about the vertical aperture. So it doesn't actually do anything for us except drawing something on the 3D. But it doesn't play a role in any way in the renderer. So it's linked. And our image plane is a -1, resolution 1000 pixel. Cool. So I'm going to do step by step until we're going to achieve our final result. So first thing to see, of course, sorry. First of all, as you can see, we have different origins issue. Our 3D origin thing is basically started at the center of our image. This is our 0, 0, as we know. So plus, minus, of course. And our 2D origin thing is, of course, at the bottom, as we know. So clearly the first step is to do some sort of an offset. Just for you to know, in different 2D packages, OpenGL, Windows, or whatever, it's not always the case. Like After Effects, I think it's always from top to bottom as well. So different ones have different conventions, but it's always going to be on the corner. And I think it's related to how we read things, basically. I think because we used to read from left to right, top to bottom, this is how it was designed. So the first thing, we're going to do some sort of an offset. So what I've done is I brought this transformation over here, and it will print the expression that I'm using to do this thing. Okay, so we can see exactly what I'm doing. And the result, hopefully it would work. So again, I brought over here this, 1 second, this thing. And I'm going to just explain really briefly if you guys are not comfortable with expression and how they're doing again, because I know all of you feel comfortable with that. But essentially, if you press the equal key over here, you can write some expression, and you get some information, and it will convert to value. I'm sure all of you know it, but I will try to break it down for us. So this will actually represent our conversion from the 3D screen into the 2D space. And the first thing we want to do to kind of like align them is, of course, add some offset. And the offset is center of the screen, which means we want to have exactly the middle of the width and the middle of the height, right? That's going to be basically our first offset that we want to use. So let's go over here. And I don't know why it's going all the way over there. And if I'll just write over here with, divide by 2. So with, of course, will give me the resolution that our input is using. And this is 1K I wrote. I just created this thing. It's exactly 1000 pixels. I'll divide it by half. And I'll do height as well, divide by f. It will give me exactly the middle of the screen, enter. So this is our first thing. It's as easy as possible. And those things are aligned. We can see exactly the 3D element, the y and x, and our 2D thing. So this is the first thing that we have to think about. The next step, let's try to, of course, connect our axis. And for that, as you can see, my axis name is axis 3. So you can see, I don't know, can you guys see the font over here, or is it too small? Yeah? Okay. Or should I make it bigger? Yeah?
We can see, yeah.
Great. Okay, so for the second thing that we basically want to control over here is I'm going to just directly link the x and y. So as you can see, I still have the width divided by half, height divided by half. So again, we are in the offset, we're in the center. And now I'm going to add the x and y value, okay, of this axis. As I explained, right now it's on -1 from the camera, so it kind of like represents our image plane, where everything kind of like converges to the most kind of like the focal plane, I guess it would be. And I'm just connecting it directly. So I'm literally taking the x and y from here, okay? To do that, if you don't know, again, in Python, I'm literally calling the name of this axis dot the knob that I want to use. Its name is translate, and dot the component of it. This is x, y, and z, of course. So that's what I'm doing over here. I'm just literally calling it x, y, and width and height. So those things are linked. So now when I'm going to move over here, you can see how, I don't know if you can see because it's a very small unit, but it's moving, right? And it's controlled by the axis. Great. Now, as you can see, of course, it doesn't align to anything. If I'm going to open over here our viewer, I don't know if you can actually see it. Yeah, our axis is somewhere over here. You can see it's on 0.5, and clearly it's not aligned. So obviously there is a scale issue over here. And I chose, as I said before, a very typical focal plane, focal distance actually, on 1-on-1. As you can see, it's very unique. It basically tells that basically on half and half, it's going to be on the corner. So minus half on the x is going to be this corner, minus half is going to be on this corner, and of course again on this. So it's kind of convenient for us. It means that basically, hey Tony, good morning. Tony. So anyway, for us it's very convenient, so it means we just have to somehow add this offset, right? And so when it's going to be at half over here. So half and half, it just means we're going to multiply again with our width, because with multiplying half, it's half of it. So we're going to reach basically our limitation of the screen, our boundaries, which is direction, right? Does it make sense? No? Did I talk too quick? Yeah. I just said again. So basically, right now we are at the center of the screen, right? We add the offset Itamar, right? So now to reach, we could, okay, I'll do it like that. Sorry. If I'll put on the axis half over here, okay, this is just our axis. We can see where it is on the screen space, right? We want to align our 2D point to be exactly where it is. So we see right now this one is reaching the edge of our plane. Sorry, the edge of our basically image. So this is actually, this point in X is going to be the entire width, right? So to jump from here to here, we have to add another half of width, right? Because we're already half of a width. So, and this value, you can see it's half. So half times width, it's half a width, right? Basically, it's width divided by 2, right? So basically half, right? It's 0.5 is half. Yeah. So we're halving the width. It means we're going to jump from here to here. Does it make sense? So if I'll do it over here, you can see I'm telling it, just take the axis, x, and multiply it by width, and take the y, and I'm going to explain why I'm doing it again with width and not with height in a second. And then we're going to add the offset. So when we looked from here, and I'm going to bring the axis, we can see that when we are over here at -5, okay, we're going from the, okay, sorry, I don't want to confuse you. Okay, over here. We started from here, right? 0, 0, right? Like that. And you can see the values over here, right? And as I'm going to jump to the half over here, a half, it's going to be the edge of our screen, right? Which means basically we just added another half of a width. So now this value gives us the full width. Does it make sense? And this is basically, of course, on the y as well, because we are using a very simple, resolution. So it's 1,000 pixels in all directions. Okay. So it means that if I'm going to go over here, now they're both always going to be aligned, right? On this specific case, because it's just a multiplier of our width and height, basically. So great, now we have this thing working. So we added this extra element. And of course, it's going to work on all direction. Are you sure it makes sense?
Yep.
Yeah? Cool. Yeah. Okay, cool. Next. So now we're going to have, actually, what did I want to show over here? I had a point. Is it this one? Yeah, I think that actually what I want to explain over here is the concept of normalization, which is not so special, but it comes again and again when you want to link different things. Don't be afraid, Itamar. I can see your face. But actually, if you're coming from After Effects, I'm sure you know this concept. And that's what I was trying to explain over here. The entire concept of what I was trying to do is I was trying to have a very simple case of kind of like normalized space. And normalized for us means that it's going to be in the range of 0 and 1. And when we have this case, so when we have one value and we can somehow convert it to be between 0 and 1, we can then convert it to be on different units. So I was trying to do like a very simple case just to explain. And this is actually what I was doing over here with the two axes. I created this sphere over here. Let me just, I think it's like that. Yeah. So I created this sphere over here, and I created a bar over here. So I have this bar, and it's started to actually from here. And I have another thing that I can actually drive. So I can literally just go over here, and if I could, it would be amazing. Yeah, I can actually drive it like left and right. And I wanted to do something that would actually drive this sphere color. That's what I was talking about, normalization. That's what I was trying to explain before, so I'm just going to dive slightly deeper. I wanted to do that basically as I'm at 0, our sphere would become basically black. And as I'm going to go all the way to the full range of the width, it's going to be like fully bright and white, okay? So this is what we'll do in different software to link different things. So the concept is basically if I bring a grade node over here, I can literally link those two, right? So I can, if you don't know, you can just press Control and just link them. So if I'm going to put 0, it's going to be on 0. And as you can see, the sphere disappeared, right? And what I say by normalization is that we know that I wanted it to be only 1 over here. So in order for it to be 1, right, which is the full width, I have to divide it with the width, right? So when I'm doing divide, it will reach a 1 only when it's going to be over here. So when I'm doing that, I can literally drive the sphere color, right? Let's do it even more interesting. Yeah, let's do it like that. Yeah, so now we have this sphere kind of like driven. And now that we have a 1, we can of course do different calculation on that to convert to different space. Maybe I want to convert to rotation or whatnot. And this is a very simple concept, I'm sure all of you knows, but that's exactly what I'm doing over here. That's what I was trying to explain. So this axis is a very unique case when it's going to be on a normalized kind of like space. It's kind of like 1 unit, 0 to 1. In our case, it's minus half to half, okay? So all I have to do is just, again, multiply to what I want it to be used, okay? So that's what I just want to show over here. Very simple case. Of course, this is like a very unique case, and it's not going to be like that in the real world. The real world, we're going to have different focal lengths and a different aperture. So if I'm going to bring over here, this is our just normal thing. Is it already working? Yeah, it's already working. Let's show it over here. Okay, 1 second. Okay. So again, in this case, I have our 3D point, our 2D point over here, and let's just put it somewhere roughly interesting. And of course, I just chose this unique thing, but in the real world, we're going to have something basically like a different FOV, different angle of view. This is just the normal nuke thing, and as you can see, it doesn't align anymore. This is our 3D, this is our 2D. It doesn't work with them. And of course, we want to use it. So now this is our second thing that we have to add to this equation. And this is just a multiplier, as you can see. But of course, this multiplier that drives the 3D point over here is not just the focal length, it's also the aperture. So we have actually two values that control kind of like basically a zoom-in effect that scale away the element, our point in space. In order to add it, so as you can see, I'm kind of like multiplying thin. We're just going to multiply another value over here. I just decided to call it length ratio. And actually, I think I prepared it over here. Let's see if I have it here. So just to make sense of things, which I'm not sure why we don't see the entire full thing. 1 second. I'm just going to remain constant because I don't see the entire resolution for some reason. I'll probably change things. Yeah. So if this is our camera from the top, right? And we have this kind of like FOV or whatever, just to understand actually what we're going to do to use those two values, which kind of like are very straightforward. I'm going to split it in half, right? So it's still this is our camera from above. Our focal distance is actually this line, okay? So this value over here, this focal length, focal distance, is this line basically from the camera, or basically the pinhole to the sensor. And it's a bit, I think, confusing on this image, but basically if you had a pinhole camera and a camera obscura, it's the same concept. So when you have a pinhole basically coming in, it's going to be aligned on some wall over here. So it's going to be like a sensor and the point in. And the distance between them is going to be basically our focal length. And this is going to be our aperture, horizontal aperture, so just this line. So those two basically lines are just measurements of different sides of angles. And if you think about it, when we change the length of it, so we're going to make it shorter, this still have to stay the same triangle, right? Oh, a triangle, sorry, not the same triangle. But as we're making it shorter, our angle over here is going to get wider and wider, right? So if I'm going to basically draw more triangles over here, so this is our kind of like F, and this is our horizontal aperture. If I'm going to make this line shorter, let's say to create this triangle or this triangle, our angle is wider, right? Our lines goes to this direction. They're opening much more. And that's of course what's changing our zoom element. So to use this value, we just have to divide those two things. So basically it's a ratio thing. It's a ratio between our f of v of how much things are open, are just a ratio between this line and this line. And I didn't want to go fully into mathematics. I'll just say, if you remember from mathematics classes when you were younger, sometimes I prefer to use f of v again, which is an angle. But as you can see, it's the same thing. It's two measurements of the same thing. This measure this opening in an angle, degrees in our case, and this is kind of like just measured with kind of like a length of a triangle. But they're same triangle for us, and they are both dictating how much it's open or closed. So if you remember for mathematics, the ratio between this and this can compute this angle. That's actually what we're doing if you want to convert between them. That's why we need those two. In theory, we have to divide this guy in half, so we can look at only this side, and it's just this over this, just to have this 90 degrees angle triangle. But it doesn't really matter for us. So after confusing you a lot, to get this scale factor, do it again. Sorry. I think it's over here. What I'm doing is literally just taking the aperture values over here and dividing it with this guy. So this over this. Actually, sorry, the other around. For our case, sorry. It's focal divided by this in our case right now. Okay, so when we're dividing it, I'll do the other around. If I'm not wrong, I think I'm not wrong. And it will give us this kind of like factor. I don't know if you can see it. I think it's too small, this one, right? I don't know if you can see it. Yeah. Yeah. And at this stage, by the way, I decided to just go and do something a bit more convenient for us, which I'll explain in a minute why I've done that. But I just created over here our own knobs. The main reason is because a lot of the time we are not going to be connected. Like maybe we're going to have a reconcile floating somewhere, which means we cannot pick up the right width and resolution, basically, of our element. And you can see later on it's actually kind of confusing. So I decided to create our own knobs. So I created this kind of like knob that holds the resolution, the offset, which is half of the resolution, and the length ratio, which again is just taking the camera and it's doing focal divided by aperture. Okay? Just so we can see, I don't know if it's going to work because I noticed no, it doesn't, for some reason it doesn't show us on the fly the values changing over here. I don't know exactly why. Maybe Adrian knows. I guess you can't really see, it's too small, but basically you can see how those two ratios kind of like affecting this thing. That's actually what we wanted. And the special case, when I had before 1 and 1, just gave us kind of like a focal plane of 1. That's why we didn't care about it. Otherwise it was normalized. Because it was basically 1 over 1. So it's just 1. It also works with, of course, other values if I would use as well. So it's the convenience because it's just this over this. Again, so now we have this point, and I'm going to add it to this equation. So now, as you can see, the aligning. And again, we have the axis, the x, y of the axis, and the y of it, multiplied with the resolution, width and height. I'm going to do actually width in a second over here, and then the length ratio that we have. So we have kind of like two different scale factor, right? A factor, the resolution of our image, and of course the zoom of the camera, and of course the offset to convert from offset of a 3D space into the 2D space. And of course, when we have that, we have a working axis. I'm going to open this one, and as I'm going to change the focal length or aperture, it's still going to align. So is this making sense to everybody? We sure?
Yes. Question.
Yep.
Yeah.
If you're changing the right now, basically, if we stop using basically a resolution like 1:1, as you have like 1,000 pixels.
Now it will work already. So I think
it should work. Yeah.
As I can see, yeah, I can see that it's actually working, right? So this is this one over here.
Yep. Yeah.
Yeah, and I'm using the 2D thing. So actually it's still working.
Mm-hmm.
I wasn't sure if it will work because it shouldn't work. I don't know exactly why it's working because this is still the old. If you would get it to the right resolution, it should still work. I'm going to show it in a second. It will be, I think, the next step. Yeah?
When you did the calculation for the FOV, shouldn't you divide the horizontal aperture by 2?
What I'm doing over here,
Yeah.
this one over this. There is a case that it's the other way around. I think in our case it's like that. Wait, I had a thing about it as well. What, I forgot about it right now. I'll come back in a second to it, okay? Because I think I forgot what I want to say about it. But absolutely right. In some cases, the other way around. Also, I don't actually divide by half, which I actually should as well. But I'll get to it in a second. Hopefully I'll get back to this, and if not, just remind me later on, okay?
Okay, that's fine. Thank you.
Okay. Yeah. Okay. So that's what Alexei asked about the resolution over here. And in this case, I just put a sphere over here in the 3D scene so we can actually see our axis in a better way. And now we have this, and as I said before, now that we can remove it, basically, I don't have the unique scene. I'm going to be at a 2K resolution. All I have to change is, again, just put it the right width, the right height. The offset is half of this and half of this, okay? And everything basically stays the same. But I just wanted to mention before, that's what I didn't talk about, is the resolution. As you can see, I'm using on both of the factor x and y, resolution of width. And the reason that I said it before is because Nuke doesn't care about the vertical aperture. As you can see, when I'm doing that, it doesn't change anything. The only thing it changes is only on the OpenGL over here. So it doesn't have any effect on the render at all. Maybe if you use a different renderer that actually cares about it, but not in the scanner render. So this means that if we're going to go back to our square thing, and I'm going to open this, and I'm going to put half and half over here. Sorry, I'm going to put it on, I think, 1 and 1, so we can see it working. Yeah. In this case, as you can see, half and half, it's only because on this resolution. If I'm going to bring a different resolution over here, I'm just going to make the height of it a bit shorter. Format. And I'm going to scale only the Y. As you can see, if we have kind of like this image, which is basically 1000 width and 700 on the height, our axis half is still actually above, right? So as I said before, I'm kind of like normalizing it before and then multiply it with the right values, right? So to the width, this reached the half, so multiply it with half, it's reached over here. But if I'm going to multiply this half, basically the width and this value, it's not going to align anymore because this is not half anymore. The half is above it, right? So wait, I'll do it like that. This point over here right now is somewhere on 0.35, okay? It's just because of our ratio. So it means I cannot just multiply it with the height. It doesn't work anymore. This normalization that I was trying to explain before, this concept of like convert one to the other, this is not normalized anymore for us. So, and the reason for it is because Nuke doesn't care about our vertical aperture. So as you can see, too many properties, sorry. I got lost in all of them. So as you can see, our 0.5 is kind of like in this, it's not almost, it's exactly the same distance as if it was the width over here. So it's basically kind of like a square thing. Okay, so this distance is also this distance. It's a square thing. Does it make sense?
Sorry,
or did it confuse you?
Yes, but isn't it because your project settings are square? So
yeah.
If you change the project settings to the 1000 to 700, then the half would be the 3.5.
No, it doesn't care. This, it's kind of like, because it doesn't use this as a factor. As you can see, the width changed the factor, the focal, it's actually using it, I don't know if it's not correct to say diagonal aperture, but basically it doesn't care about this height factor. It doesn't change anything, which in other system it would.
Not even in, because we're having the width, the height, and
yeah.
height
no.
is,
this actually creates a lot of confusion even when you do like p-word and try to convert them, because it's kind of like a bit confusing. But as you can see, I'm point half, right? So it's kind of like the same, it's half, but it doesn't align. This would only align if it's going to be basically 1K over here as well. So this doesn't change.
Your project settings is still...
No, but this is picking up from this sorry, maybe I should have shown it. I'm using this constant that drives the format of this 3D system. right?
Yes, but when you're writing half of height is driven by the project setting.
No, it's driven by
No, it's driven by this, by the input. If I would not do it, if I would take it out, then it would be driven. And by the way, you can still see it, that it's still half over here. So the resolution doesn't define anything in the 3D system. It's just kind of like a scaling factor. This is still going to sit on the half, no matter which format is going to be over here, in this specific FOV of 111. Okay? In this specific case, no matter which format I'll put in, it's just a scale factor for it. It doesn't care. This, I'll put it like that. You can see that it's reaching basically the limit over here in the half, right? And no matter what I'm going to plug in, I have right now 2K. It's still half. I'm going to plug in the 1K that I had before. It's still on the half. It doesn't care about it. It's just a scale factor.
Yes, but I'm kind of confused by that also, because if you're writing an expression and writing width and height, it's just picking up the project settings, isn't it? Not what is upstream.
You mean without this, you mean?
No, if you have just any expression and anywhere and width and height should be.
You mean because of what I'm using over here?
Yeah.
No. I'm not even talking. I'm talking like even one step before. We cannot just use any width. That's what I said. That's why I'm actually using. That's why this is incorrect. That's why I cannot just do resolution width and resolution height. You're right about this. I'm talking about even one step before. I'm talking about the concept of normalization, right? I need my axis to be in kind of like a normalized state, right? To be in kind of like half and half, to multiply it with the resolution. But what I'm getting from you is not normalized, right? Because my half is not actually aligned to the height anymore. It doesn't align to our format anymore because of this. Does it make sense, or maybe I confused you even more?
Yes.
So this is basically, I'm just still talking about the 3D system and how it's basically, we cannot use it directly, because what we're getting from the 3D system is not going to be aligned anyway to what we're going to do in the 2D.
Yeah.
So it's before, I'm not even talking about this. You're absolutely right about this. I'm talking it no matter which format is going to come in, as you can see, the ratio is always going to be the same thing. When the half on the sides in this specific focal length, it's always going to be half over here, no matter which format I'm going to put in. So it means it's normalized for us. I can multiply always by half and it will work. That's great. But the height would not work.
Yeah,
because... Right?
Yeah.
Okay. Is that okay, Tamar? Yeah? So I'm just saying that it doesn't squash it, basically. But if I'm going to put like one over here, it doesn't squash our thing to be over here at half. Like kind of like if it would be like different sensor or different lens or whatever. It doesn't do, I don't know if it's correct even to see it on the sensor as well, but it's the lens. But it doesn't give us normalized thing. That's what I was trying to say. So we cannot just use it. And it's basically a square. This is going to be half, this is going to be half. So we always going to multiply. Yeah, Adrian wrote. What did you write? Sorry, can you say it? I missed out. Input width, yeah?
Just in case.
Yeah, absolutely. Yeah, so Adrian is basically just saying input width is going to be the input, of course, and the root width is going to be the format. That's correct as well to say it. Which I don't write, I just write width, which is not clever. And I'm going to show it in 1 second as well why it's actually tricky to even use it on the axis. By the way, axis, I'm going to try it on, I want to show it in a second, but sometimes when we want to convert values from this axis, and I'm going to use the width over here to do multiply, I'm going to get, I don't know if you can see it on the screen, it's 640. It's not the root format, and it doesn't have any input because this is a 3D node. So it doesn't have any input of image. And a lot of time when I used to do it on tools like that, in the beginning I was really confused because I was like, wait, what doesn't work? And then I'm writing width, what's the wrong? And then if you just look at the width, you see that actually it's using, I think it's using this format internally, if I'm not mistaken. It's using, I think, this format as a default, the PC view over here. Yeah. So just for you to know, so you don't make any mistakes. And if I'm going to try what Adrian is saying, root width, yeah, we're going to get exactly the format of the project. So that will be actually more correct. So does it make sense what I just said? So basically, because it's kind of like a square thing, right? You can think about it as you don't care, we only care about the width. We always have to multiply now with the width over here. The special case is if you're gonna have a different aspect ratio. This would actually make it squash. Not over here, it's still gonna be like that. So we just have to take it into account as well, which I'll show a bit later if we'll have time. But
Different pixel aspect ratio, or
the pixel, yeah, like you see, like this two over here, or this point.
pixel aspect ratio.
Exactly,
yeah.
This is another squash. It doesn't change the width again. It's we only care about because of the height. Again, because we have this square thing, so we have to kind of like accommodate to how much we're scaling things. So we have to just add it to the equation. So as you can see, I'm doing that. X, Y, resolution of width, right? We're multiplying with kind of like normalize. Factor of the length ratio, because we wanted to have it like on one, basically. And then an offset. So now we have basically a very cool basic reconcile. And this is our 3D. This is our 2D over here. The align, everything is great. Cool. Next step is, of course, the depth. Now, we're not going to be so convenient in real life to have axis that it's only on -1 exactly in real world cases. So if I'm going to, of course, put it on 2 or higher than that, we're going to have things that don't align anymore. Our 3D doesn't align to our 2D. So of course we're going to add it to the equation, and it's very simple. It's another scale factor. As you can see, if I'm going to put a point over here somewhere, maybe like that. As you can see, as I'm scaling as I'm actually adding the depth, so I'm pushing it back in the depth over here, the 3D point, will get converged to the center of the screen, of course, on the X and Y equally, right? So we know it actually drives both of them. And this is, again, a scale factor with the depth. We know as things are basically far away from us, they would move less in our eyes because, and again, it's a scale factor of the distance. As they're getting closer, they will move more. So, of course, the trick is just to use the Z over here, which we haven't used in our equation. We only use the X and Y. So the next thing is actually to introduce the Z in this equation. I think it's over here, yeah. And all we have to do is just divide it with the Z. That will normalize it again to be on the -1 of the plane. So basically, we want to divide those two with the value over here, right? This would force to be on the image plane of -1 all the time. And it will scale the X and Y accordingly, right? So as I'm pushing it from Z back to me, I would scale it as well to be aligned with that, right? So if I'm going to go over here, and I have this axis, I don't know if you can see it on your screen. You can see it over here. I'm just going to call the Z like that. And I'm just going to call the Z over here. So now I'm dividing those two. And of course, I fucked something up as usual. I think it's my width and height that is incorrect. No? What did I fucked up as usual? Ah, sorry.
Minus?
Yes, exactly, minus. Sorry, yes, I forgot about that. Thank you very much for that. It is minus. And the reason that it's minus, by the way, wait, over here, yes. So now if I'm going to push it into Z, now we have a scale factor, and the Z is working as well. So even if we have different points and they are at a different depth, it's still working for us, right? Now, the reason that I said that it's basically minus, I forgot about it. Thank you about it. Is it Itamar? The reason that it's a minus is because theoretically, if it was a camera obscura, kind of like a pinhole thing, the image would sit over here behind, and we are basically want to flip it to be in the front. That's why we actually take the Z of the minus. Actually, everything is mirrored. That's why. So we are kind of like mimicking to put the image plane over here, which is not. It's supposed to be actually over here in the back. So because we're flipping it, we're actually doing a minus over here. If it makes sense.
We're looking at the back.
Yeah, I mean, if we look at the camera obscura, pinhole camera, the image plane actually, the rays goes like that, right? It's kind of like a mirror thing. It's flipped. Everything is flipped. But we are putting the image plane for us over here in the front of the camera to see everything. So it's kind of like minus that to put it over here in the front of it. Sorry.
Yeah.
So in that in mind, now we basically have a almost fully 3D point to 2D. So we took the focal length and the aperture, the format scale, and the depth. I think I haven't forgot anything. So now we have basically everything inside. Does anybody have any question up until now?
So I think there are 2 points in 3D space that can produce the same point in 2D.
You think there are 3D points in 3D space?
Two 3D space points that can produce the same output in 2D.
Probably one in front of it and one behind you.
Behind the camera, yes.
Yeah.
But
So
there's an infinite amount that can do that.
So that's why
Sorry.
I'll show it in a second, but that's why we're gonna, every time we do a renderer or basically like scanner renderer, we always check the component of the Z. That's why, by the way, I didn't have time to, I don't know if I'll have time to reach it. That's why when we use basically our distance, our depth channel over here that comes from the scan line, if I look over here, right? Our depth channel is not a distance function. It's just the Z component. In fact, it's just this value. It's just this guy. And that's why I wanted to show that the most basic thing is this case of like -1. Because rasterizers, on most systems actually, they would cancel the camera, which is what I'm going to show next, and then they just use this component to give us the depth. So it's kind of like always kind of like an image plane. So when we want to render, we check if it's basically a positive value, it means it's behind us. In this case, and we won't render that, or we won't actually touch this polygon or vertex or whatever. Everything that's over here, we will see. That's how we'll kind of like, it's a very simple test to do, and we'll see it in a second. So of course, one of the benefits of using this system, which I clearly, as an idiot, already baked it over here, I'll just copy it over here, is if you're going to have a reconcile over here, and we're just going to look at over here, we have this point, we have an axis. I'm going to plug the usual reconcile and camera and axis, and we have the same calculate like that live. We have the point, I don't know if you can see it on your screen, but it's over here. And this is, sorry, this is a baked one, because I mean, is this a baked one? What did I forget again? What this time I forgot? Probably something is not linked properly. One second.
I think it's linked to the other axis.
Yeah, absolutely right. Thank you. So, you know what? I'll just copy the entire thing. Cool. Okay. So again, now if we actually, no, I wanted to have that axis as well. I'll do it like that. Ah, it will not work.
Change the name.
Fine, I will. Gosh. Okay, I'll do it just like that. It's okay. Okay, so now when we have that, I added this axis over here. And I think it's very tiny. So let's put it a bit bigger. Bigger! I don't know if you can see it. Yeah, it's over here. And I just had this random kind of like thing over here for it to kind of like move over the screen. And you can see our 2D point over here. It's always aligning with that, even though we have a different depth. And I just want to show that the benefit, one benefit of many, is if you're going to plug, of course, a reconcile in the same thing, axis and camera. And if I'm going to bake this, of course, it will have to run for the entire thing. And if you have a 3D system or whatever, it's a bit slower. And this is the benefit of that is just you can just go over here and just do edit, generate, done. And this is just one benefit of that. So it's just, you don't have to wait for it. There are other benefits to do that. One of the things that I like is basically to have a separation thing. So when I have just this, I can actually bring different points and just as a position or maybe just a scale. Before I'm going to go to the next thing, okay, this is our bake over here, is of course, I forgot the most important thing, is the camera is not going to be at the 0, 0. Is this the next thing? Yeah. So if I'm going to have over here, I just put a point over here in space, and I have a camera that basically is moving around. Okay, it's kind of like, so this point is kind of like moving all around, and our camera is also moving, and I think I also add some FOV, I think, in the other example. We'll see it in a second. And in order to kind of like avoid that, again, I think the first time when I learned 3D systems, it was very confusing for me because I didn't think of that system. I'll add again. I kind of like always thought that only when I'm looked from here, the scene is being rendered in my head. You know, it was a bit confusing, but essentially every time, every view is basically a camera, right? Even this hidden camera. And to do that, every rasterizer, this is a rasterizer, a scanner render. It's a group of different engines that kind of like render everything not in a ray tracer way. They would basically shift everything to be aligned to a camera view. That's the things, always. So essentially, they are canceling the camera. So we're taking the position of the camera, taking the inverse of it, multiplying with all the vertices. So now it's canceling the camera. Everything is now moving the same ratio with the camera. The camera is at 0, 0. And then we can do all the rest thing that we've done. So, because now our -1 or our minus whatever Z is aligned to the right image plane of the camera. It doesn't kind of like orient in a different position, which now the Z would not make any sense to us. So in this way, everything makes sense to us. It's kind of like a line is parallel to the camera. It's very convenient. The numbers is very comfortable for us. So in this case, I'll just hide this. Yeah. That's what I said. I have a camera that's kind of like moving over here. It doesn't move. Why it doesn't move? I have no idea why it doesn't move. Because I have no idea why. Doesn't matter. Right now, just for the demonstration. In order to avoid, anyway, it's not in the center, it's not in the center anyway. So our goal is kind of like move it to the center. But we want to move everything with that. We want everything to stay in the same relationship, right? We're just rotating together. So to do that, we can either use Tony's brilliant inverse axis, which I don't have, unfortunately. So I have my own. Sorry about that. Because I'm on not on your Trickster machine. And as you can see, I have kind of like, I duplicated that. So I have one sphere over here in the camera. This is my scene. And I created just a duplication. But in this case, I have an axis that is being linked to this camera. The camera that is not in the 0, 0. Okay? And this guy will basically invert our movement. So if I'm going to look over here, as you can see, everything shifted. So this is our scene. And when I'm doing that, our camera is at 0, 0. Everything is in the same relationship. If I would render it right now, everything would look the same. You would not know, right? But it's not in the same place in our world position. And that's what I said when I first learned that. It was very confusing for me to think that actually everything right now is kind of like shifted. We just don't think about it because it gives the illusion in a very nice way. But everything is always kind of like aligning. The camera right now is 0, 0 basically, and all the world is now shifting to be like that. So when we do that, if we look at those values over here, this would actually show us how everything would be if the camera is at 0, 0. Without it, it's the same axis as this. You wouldn't see it over here because it will not change the value over here, but it does change the world metrics. So when it actually shifts. Now, if you remember, I don't know how many of you were in the other class, but I just looked at those values over here. Those 3 are aligned to our X, Y, and Z. Our world metrics. So if we're going to concatenate different matrices, those 3 would actually align to new X, Y, and Z. So we're now going to use those guys and not this guy. Okay? So with that in mind, now we have actually a point that is moving. And we have this that even though the camera is moving in its different location, it still aligns. So now we have camera moving, FOV, depth, and everything together. I think I had a case over here. Yeah. Maybe it's this one. Yeah. It's not this one. I can't even remember which one is which. Sorry, it's too many nodes. Yeah, and everything is aligned, even though our camera is not in the right location, and it's moving, and whatever, everything is working. I think we are running out of time. I think there was a few more things that I want to show you.
Eyal?
Yeah?
I wanted to come back to the inverse of the camera.
Yes.
Because I think that's the point that is, because we need to understand how we're doing that, and not all of us will have all the time tool of someone. And I think that's, if I'm not mistaken, it's you just taking the animation of the camera and adding the minus to everything, and also changing the rotation order.
Yeah, so I didn't do it. No, my tool this is actually doing inverse of axis. Actually, there is equation over here inside. But yes, if you wanna convert that, if you wanna basically swap it, then yes, one way to do it without any tools is to go and do minus over here on all of them. So basically flip the sign and then flip the order. So if it's ZXY, do YXZ, and that should actually also give you kind of like the inverse animation of that, and then you can plug it in. Another way is to use Tony. That's why I said the Tony tool. You can also use mine if you want. You're welcome to use. I think Tony is going to work in all cases. Mine, it doesn't work in all cases. Mine only works when you have rotation and position. It doesn't work if you have scale or skew.
But usually scale of skew, it's not important for you anyway.
For the camera, again, if you're using different axes and concatenation of things, maybe it's important. I don't know. Yeah, camera. That's why this specific thing. This is actually inverting camera specifically. This node, because I know I don't need it. Unfortunately, Nuke doesn't come with a built-in inverse axis for some reason. It would be amazing, but it doesn't. So I didn't have time to go deep into this inverse thing. That's why I kept it in a different lecture about the matrices. Yeah, so you have to just take my word for it, but basically you want to inverse it. So this is kind of like 3 ways that you can do it. Tony, this tool, or as you said before, of course, negate all those signs over here and flip the order of the rotation. If you have, by the way, a few, because sometimes maybe you have an axis that drive this, by the way, so you cannot just flip those signs. So in this case, it wouldn't work. That's the issue.
I do understand. I just want to, because so far we completely, like it's all clear and clean with the, okay, we just have axes, and this is the math. And I just want to kind of like to really to point that this inverse, because like now it's drawing, oh, we need some additional tool and stuff. So we can just use simple axis when we're just really negating the values of the camera and negating the order of transformation and rotation, and that's how we bring it to 0, 0, 0. And then you're staying with the basic tools. I understand it will not work when you have additional axes.
It will work. Actually, you know what? I will explain it in a minute. Actually, it will be maybe easier. If you do have concatenation axis and you do want to make it work, it's tricky, not because it's complicated, it's just a bit annoying to do it like that. Let's say I have like 3 axes over here and I want to flip the order. Let's say this one doesn't have any animation. Everything is driven by those guys. Do the same thing. Negate all the values of the position and rotation, flip this sign, and also flip the order of the axis. And that would also do the same effect. So if this is 1, 2, 3, make it basically 1, sorry, what did I place? Yeah, 1, 2, and 3. This will also give you the inverse as well. So you don't even have to do that as well. You just have to make sure that it's not on the camera. So a lot of the time what I do, I like to separate those two. I like to have the camera which only holds the camera information and the animation on the axis, because that allows me to invert things quite quickly if I want to. So in that case, I would actually just flip everything, and that would still work. And you can still plug it over here, and it will drive it, and it will work perfectly fine as well.
Yeah, right.
Does it make sense?
Yeah.
So I don't think we have time to go into the math of it or whatever, but does everything make sense? I just want to understand the concept of we have to invert the camera. So we're not just looking at the location anymore of the axis. We first have to cancel the camera movement. And by doing that, we actually invert everything in the world and put the camera at 0, 0. So now everything is aligned to the 0, 0. And in that way, now we can use all the values that we have in the axis, vertices, or whatever. Does it make sense?
Yeah.
I'll just wrap it up because I don't think we have any time. This is all together.
We're out because people need to go to morning meeting.
Can I just say 2 more things, just to inspire? So 2 more things. One is that the reason that I chose this topic, and I think to some of you it makes a lot of sense, is that this Reconcile thing, only because it's Reconcile for Nuke, it's the bridge between 3D and 2D. This is the core of everything. Every engine out there have to do some kind of like projection of a 3D point into 2D point. And us is basically the bridge between 3D and 2D. I think it's extremely important. We don't have time, but what I want to show is basically we can also do the same thing in image. So if I would have 1 pixel value over here that holds some information, in this case it's just 0, 0, minus 1. So just the first case that we have, I can still actually print it into the screen as a value, and I created this kind of like nodes that does the same thing. So if I would do the same thing in the math nodes over here, it's the same thing basically. I'm having this 1 over z, I have a scale factor, of the FOV, I have the resolution factor, and I'm doing the offset, same thing that I explained before. And I have a Blink script that actually would print it in the 0, 0. So now if I'll go and change those values, I have basically this kind of like point. This means basically that now you have essentially a point renderer. It's the same thing. So now if I'm going to push this, that's what I want to show before, I created this kind of like image, put noise value, just noise of like -half to half on different values, red, green, and blue, right? Have the same expression. It's literally the same thing that I'm doing over here. This expression and expression is now over here in nodes. And I have a Blink that just takes those values and plot them into the screen. So now basically we have a point renderer. It's the same thing. And this is the core of everything. That's why it's not just a reconcile. It's literally everything that we are doing. And that's what I want to show you, that basically it was such a simple thing, but that the core is basically building up to this thing that you can do. And this is just a simple thing, of course. And it took like, I think, half an hour to kind of like wrap everything up in this one. So it wasn't such a big deal. And you can build up on that, do kind of like filtering or whatever. Maybe we'll do another work class on the other half. The other half was basically how to convert 2D points into a 3D points. So maybe if we'll have time, I'll do it next time. If there will be any interest, but this kind of like wouldn't be the reverse order of it. So we took 3D point into 2D screen, and we also want to do the other way around as well. If we have a 2D elements or 2D point, we want to find it in 3D space, and what will be the benefit of it as well. Anything else?
Thank you, Eyal. Pretty cool.
Cool.
Thank you very much.
Thank you all.
Thank you.
Have a good one.
Thank you.
Bye-bye.
Bye-bye.
Thank you.
So,
And stop recording.
Oh yeah, yes. I actually was recording probably, yes.
You're recording as well?
Yeah. Recording on my side and manage recording and stop recording.
Oh.